And the second task I gave you was on this sheet that's titled concentration. You have two beakers here, beaker on the left, beaker A, beaker on the right, beaker B. You see that beaker A has got more of these blue particles in beaker A compared to beaker B. The number of light blue particles remains the same. Now, what you see with this question is which beaker is the most concentrated, and explain your choice. Now, by just looking at beaker A, I can see there are more blue particles. So I'm considering beaker A is more concentrated with these blue particles. Now, because we're talking about acids and alkalis, I'm assuming that these blue particles reflect either acid particles or alkali particles. So if you have more blue particles or more acid particles, then beaker A is more concentrated with acid particles, or if you had these blue particles here representing alkali particles, then beaker A will be a more concentrated alkali solution. So that's the reasoning behind why beaker A is more concentrated, more particles in that same given volume of liquid. Now, question 2, this chemical reaction we have done in lesson as the year has progressed. So when we add magnesium to hydrochloric acid, we get magnesium chloride and hydrogen. A magnesium strip is kind of a dark grayish in color, and hydrochloric acid is a clear liquid. When hydrochloric acid reacts with this metal magnesium, what we see is the magnesium on the surface changes color to white. That white deposit is magnesium chloride. What you'll see around the white deposit is hydrogen gas, and this process is very visible. These small gas bubbles are very visible in the actual liquid. What you'll see if the magnesium strip was added to beaker A, you will see more bubbles in beaker A compared to beaker B. These bubbles represent the hydrogen gas. You will get a higher temperature in beaker A because there are more acid particles, so more reaction between the acid particles and the magnesium, creating more hydrogen gas, so more bubbles, and this is an exothermic reaction. It's giving off heat, and the test tube or the beaker will definitely increase in temperature if you were to touch it. And you will see a faster rate of reaction as well. On beaker B, you may not see as many bubbles. So how would you handle these two beakers of acid differently? Now, we've kind of discussed the answer in the previous part. So beaker A will release more hydrogen gas and release more heat. So avoid inhaling. If you're leaning over the beaker, this hydrogen gas will be rising up. So avoid inhaling this hydrogen gas. There's a distinct smell, and be cautious on touching the beaker and holding on to it, especially when you know it's going to get hot. So it may not get too hot, but there is a possibility of it getting very hot depending on the concentration of the acid. So cautious with the holding on to the beaker. It could possibly burn your fingers or your hand. Now, the end task, the last task I asked you guys to do, which was kind of a tricky task to be fair, but let's have a quick recap of what we did last lesson. We discussed acids and alkalis. Acids are chemicals. Alkalis are also chemicals, but they behave in the opposite way to acids. We get weak acids such as oranges, lemons, vinegar, and if we were to identify these acids, they would be sour to taste. That's something that you can mention in an answer in your exam. Strong acids, such as nitric acid, sulfuric acid, hydrochloric acid, are some of the acids that we use in the lab for chemical reactions. Alkalis, they behave in the opposite way to acids. Weak acids, some of the examples are like fairy liquid, soap, bicarbonate of soda, toothpaste. So what you could write in the exam that could identify weak acids, they are kind of soapy in texture, and that's something that the examiner is accepting as an answer at your stage, at your level in year 8. Strong alkalis, such as sodium hydroxide, ammonium hydroxide, and we use in the lab. Bleach that you use at home is a strong acid alkali as well. We describe them as caustic because they have a potential to burn or damage your skin. So these are the type of notes that when you were watching the video last lesson, you should have been making. Now, I asked you to find out the chemical formula for some of these acids that we had discussed. And if you have a look at the chemical formula for lemons, you got C6H8407. Origin is very similar. Vinegar, we've got the carbons, hydrogens, and oxygens. Nitric acid, we've got hydrogens, oxygens, and nitrogen. Hydrochloric acid, we've got hydrogen and chlorine, and sulfuric acid, we've got hydrogen and sulfur and oxygen. Now, if you look at the common kind of elements in acids, what you'll find is, sure, all of them contain hydrogen, so that's one of the main ones actually. The hydrogen is common in every single acid. Now this is the pattern. This is something I wanted you to spot, that it's quite easy when we look at these three, the hydrogens at the beginning of the chemical formula, whereas the weaker acids, the hydrogens are embedded within the chemical structure. Now, it's because of this hydrogen inside the acid that gives the nature of how strong it is. Something that you'll look at either at GCSE or at A level, those of you who decide to do A level chemistry, is this hydrogen dissociation factor within acids that to give rise to how strong an acid is. Alkalis, on the other hand, if you look at soap, it's got a few alkalis in it. Toothpaste has got alkali in it. These are some alkalis that we mentioned in the lesson. Now, if we look at these alkalis, what you'll spot, especially in the ones that we use in the lab, that there is an OH and hydroxide ion present in many of these alkalis. Now, that again is something that gives alkali its property. Again, as I said, with acids, it's something that you will look into much more detail when you go into GCSE or A level. Now, that's all I wanted you to spot, the similarities between one alkali to another and the similarities between one acid to another. And the final one I'll leave you with is water. So with water, what we have is we have hydrogen and oxygen. So water is neither a strong acid, is neither a strong alkali, but it does have a structure that has hydrogen and this oxygen hydrogen combination as well. So does it sit on the alkali side or does it sit on the acid side? I'll leave you to ponder that because it will become more apparent as we go on to the next lesson with pH and universal indicator.